When you build a suspension bridge, the process is intensely deterministic. The blueprint dictates the exact load-bearing capacity of every steel beam, and the final structure reflects that plan perfectly. But in building artificial intelligence, that expectation of perfect top-down engineering falls apart. We started out trying to build neural networks the exact same way. Back around 2012, machine learning researchers treated AI like a custom-built watch. They acted as master watchmakers, explicitly decreeing what every single layer should compute. Take AlexNet, the model that proved deep learning was the path forward for image recognition. Its designers forcefully dictated exactly how the network should compress spatial data. They hard-coded massive 11 by 11 feature extraction filters right at the beginning, aggressively tailoring the pipeline to fit the strict memory limits of the graphics cards they were using. That customized approach cut error rates by double digits, effectively ending hand-coded visual features, but it resulted in a highly localized machine. Because it relied heavily on human intuition, it left behind no universal rulebook for how to scale the technology further. The logical next step for the field was simply to go deeper. Researchers assumed that to get more complex AI, they just needed to take those carefully designed layers and stack them higher. This chart illustrates the degradation problem of 2015. Expanding a network to 56 layers caused its learning to crash, producing higher error rates than a 20-layer version. The optimizer got lost. Instead of passing data unaltered, incoming data was destructively rewritten at each step. Imagine having to rewrite an entire document from memory at every single stage of editing. Forcing every layer to execute a complete rewrite of the representation from scratch is mathematically exhausting and highly prone to error. The master watchmaker approach had hit a strict mathematical wall. The field realized that micromanaging the architecture of intelligence by hand simply breaks at scale. The solution arrived with the ResNet architecture and a structural mandate called residual path discipline. This design abandoned the destructive total rewrite model of earlier networks. Engineers introduced the skip connection. Data flows down an unaltered main highway, while computational layers sit off to the side. The side layer calculates a small mathematical delta, like a track changes feature, and adds that tweak back into the main flow. This simple change in wiring flattened the chaotic geometry of the training process. By protecting the original information, engineers could suddenly and reliably train networks hundreds of layers deep without them crashing. Network depth stopped behaving like a fragile chain of rewrites. It was tamed into an accumulated refinement process, governed by a sturdy mathematical scaffold. That scaffold paved the way for the transformer model. Researchers stripped away the older, domain-specific visual filters. They replaced them with self-attention algorithms, wrapped inside the exact same residual scaffold that ResNet pioneered. This created a portable, repeated block. It functions as a true tabular blank slate, agnostic to processing human language or visual images or computer code. But this raises a central question, explored in the 2019 BERT probing studies. Before deep learning, humans had to build separate software modules to handle grammar, another for sentence structure, and a third for the actual meaning. How does a uniform, repeating block handle all of that without those handcrafted compartments? The probing studies revealed that during training, the uniform layers organically specialized on their own. The lowest layers handled basic syntax, the middle layers managed structural parsing, and the highest layers took on complex semantics. By looking inside these blocks, we see that the AI rediscovered the specific stages of language humans used to spend decades trying to code. It proves that a completely governable, mathematical blank slate is infinitely more capable than any complex, hand-drawn human blueprint. With the internal blocks stabilized, the human engineer's job shifted upward. The focus moved away from designing the internal layers and toward designing the overarching environment where those identical blocks live. This chart plots a declining power law curve for model error, mapping the modern physics of scale. Researchers found that a model's intelligence maps against predictable equations, holding steady across massive expansions in parameter counts and compute budgets. But getting that math right took refinement. A milestone known as the chinchilla correction proved that many early large models were severely undertrained. Expanding a model's parameter size yields poor results unless you scale the amount of training data equally. The definition of a good architecture is no longer about a clever diagram. It is about whether a model family's behavior stays predictable across massive expansions of scale. You might look at modern mixture of experts, or MOE models, and see a contradiction. Routing data through multiple specialized subnetworks looks like a regression to the bespoke days of AlexNet. There is a vital mechanistic difference. In an MOE model, the specialization is managed entirely by an algorithmic router. Human intuition has been removed from deciding which expert handles which specific token of data. This localized complexity is safe because it remains securely contained. It is governed by the predictable physics of the external transformer scaffold. Architecture is no longer about scripting competence layer by layer. Instead, the engineer's role is to build sturdy, blank slate environments where the artificial intelligence can reliably build itself.